Hello everyone, welcome to CFD College. I'm Ashkan, and in this series of videos I'm going to solve some fluid mechanics questions, specifically uh, the assignments of fluid mechanics 1 from Concordia University will be solved in this series of videos. So if you're interested, you can follow these videos. We have lots of videos in this YouTube channel about CFD, about research. So if you like them, if you like to learn how to research, or if you want to get some advanced skills in CFD, you can subscribe the channel so that you don't miss our future videos. But let's jump to this tutorial. In this video I'm going to solve the first assignment A, which is related to chapter 1 of fluid mechanics 1, shear stress and viscosity. So we will have 5 different questions, and I'm going to solve them for you. So let's have a look at the first problem, problem 1.37 of 6th edition of Monsoon, I think. Okay, here in this, in this question we have 3 different plates. The lower plate is fixed, this one, and the other plates are moving with different velocities, v1 and v, and we know that v is greater than v1. Between these 2 plates we have 2 fluids, one with viscosity of mu and the other one has the viscosity of 2 mu. It is, as it is mentioned, it is twice as viscous as the other fluid. The distance between the top plate and the bottom one is b, and here the distance between the middle plate and the lower plate is c times b, and we know that c is smaller than 1 and greater than 0. And what should we found? We should plot the ratio of v1 over v. So this ratio, you should plot this ratio v1 over v as a function of c. Okay, so we have to plot this chart, and we also no, there is nothing else, and now we can solve the problem. Okay, let me change the color a bit. Okay, v1 and v are constant velocities, so there is no acceleration. And when there is no acceleration, you know that the summation of forces is equal to ma, and since we don't have acceleration is 0, so the summation of forces is equal to 0. On this plate, the middle one, we know that there is no acceleration. V1 is constant, so the summation of forces acting on this plate should be equal to 0. So there are two forces, one due to this fluid, and the other is due to the fluid between the middle and the bottom plate and the lower plate. And these forces are due to shear stress on both sides, and they have to be equal. So the force due to top fluid, the shear force, is equal to the shear force due to the bottom fluid. And we know that this force, these forces actually are due to shear stress. And as you know, shear stress force can be calculated as tau times area. And you know that tau can be found as mu du over dy. So the force is equal to mu du over dy times area. Area is the area of this plate. Y is this axis, always perpendicular to the flow. And for top and bottom fluid, we should find this force and make them equal. So this is equation 1. From equation 1, we can find that for the top fluid, the viscosity is 2 mu. So 2 mu du over dy for top times area of the plate. And for the bottom, viscosity is mu du over dy for bottom, and AP, area of the plate. So area of the plate can be erased from these two sides because it's the same. And also mu. So these are cancelled, and what remain is 2 du over dy for top is equal to du over dy on the bottom. Okay, as you can see here, the velocity profile, the velocity distribution is linear in both fluids, here and here. When you have a linear velocity distribution, so when, I have to, okay, let's increase the width. So when you have linear velocity profile, du over dy equals the slope of this line. So for the bottom, the slope of this line can be found as the difference of the velocity from between these 2 points, V1 minus 0 over the thickness of the fluid, which is C times B. And for the top, the difference between these velocities, V minus V1 divided by the thickness, B minus C times B. Okay, so what we will have is 2 times V minus V1, and if you factor out B, 1 divided by B times 1 minus C equals V1 over CB. Now again, you can cancel this B from both sides, and now it's easy. You can solve the you can solve this equation. 2 C times V minus V1 equals 1 minus C times V1. So 2CV equals V1 minus CV1 plus 2CV1. So 2CV equals V1 plus CV1. And now 2CV equals V1 times 1 plus C. So this ratio V1 over V equals 2C times, divided by 1 plus C. This is the equation. And if we want to plot it, we need some points. This is C, here we have C, and here we have V1 over V. So if C equals 0, V1 over V is 0. So here 0, 0. And for example, here C is 1, here is 0.5, V1 over V is 1 there. Okay, if C equals 1, V1 over V is 1. So this is one of our points. Here we have another, and for between, if C equals 0.5, V1 over V equals 2.3, 0.67 approximately. So here this is 0.5. These are our 3 points, and if you have noticed, this equation is not linear. So it's not linear, and you will have this line with a curvature towards the bottom. So this is the first equation. This is the first problem, and you can see it's easy. You just need to follow some steps to solve fluid mechanics 1 problems. The next problem 1 chapter 1, problem 80. Here in this problem we have this block. We know its mass is 10 kilograms. Slides down with smooth inclined surface. So it's a smooth inclined surface with the angle of 20 degrees. We determine the velocity of the block. So we should find this velocity. We know this gap is 0.1 millimeter between the block and the surface. We have oil, SAE 30 at 600 degrees Fahrenheit. So we can find from the tables that the viscosity of this oil is 0.38 Newton second per meter square. And here we have an assumption: velocity distribution in the gap is linear. Okay, I will get back to it. And the area of the block in contact with the oil is 0.1 meter square. So here we have gap. Gap is a key word in fluid mechanics 1. When you say this, it means that the velocity distribution in the gap is linear. So when you have gap, the velocity distribution should be linear. And in this case, you can find du over dy as the slope of this line. For example, if it's v and here we have delta, du over dy equals v divided by delta. So remember, gap means linear this velocity profile. Okay, now we want to solve this. Since this block moves, is moving downward to the left, so we will have shear stress force resisting its movement. So shear stress, which is acting on the block, is in the opposite direction of its movement. And we also have the weight of the cylinder. It's good to define the y-axis perpendicular to the surface and the movement direction, as I mentioned in previous problem. So this is y direction. Now if we draw free body diagram, we will have tau times area, and this is w, and you know that we have to decompose it into these directions. And in this direction here we have theta, which is 20 degrees, and this should be w sine of theta, and this is w cosine of theta. So since the speed of this block is constant, the summation of forces here is x in x direction is equal to ma, and we know there is no acceleration, so it's 0. So tau times area equals W sine of theta. Okay, here we have gap. So this is V, and here is the surface. This is the gap, B, with the thickness of B, and this should be the velocity profile, which is linear, and the slope of this line is V over B, which is equal to du over dy. So tau is equal to mu du over dy, area, and W is mg multiplied by the sine of theta. Okay, so mu V over B times area equals mg sine of theta, and we have all of these. This is 10 kilograms. It is gravity. We know theta, we know area, we have B and mu. So you can easily find the velocity. Velocity is equal to B mg sine of theta divided by mu times area equals B is 0.0001 meters, mass is 10 kilogram, G is 9.81 meter per second square, and sine of 20. Mu is 0.38 Newton second per square meter, and the area is 0.1 meter square. This way you can find the velocity equal, you can find the velocity 0.0883 meters per second. You can see here, this is so simple problem. Okay, next problem number 81. Here we have a layer of water flows down. So this is water. A layer of water flows down an inclined fixed surface with the velocity profile shown. So in this problem, we have the velocity profile. Actually, we have, there are some situations. One is because when you are dealing with the shear stress, you need to know the velocity profile so you can find du over dy. And there are some situations. One, they told you that there is a gap. If we have gap, it means that du over dy is velocity divided by delta. As you know, means linear velocity distribution. The second situation is when we are given the velocity profile. So velocity profile is given like what we have here. If you have the velocity profile, you can find du over dy. You just need to take the derivative. Okay, we should determine the magnitude and direction of the shearing stress that the water exerts on the fixed surface. The water exerts on the fixed surface. Uh, we know that when water is moving, or any object is moving, in this direction, the shear stress due to that surface is acting in the opposite direction. It prevents the motion. It's kind of a resistance. But here we should talk about the shear stress that the water exerts on the fixed surface. The water is moving in this direction, and the shear stress is in this direction. The shear stress from water exerts on the fixed surface. So we know that the shear stress acts on fixed surface is parallel to the flow, to the movement direction. So this is the direction. We know U, capital here, is 2 and H is 0.1 meter. This is the H. Okay, it's so we know the direction. Now we should find the magnitude. It's easy, as you know. Shear stress is equal to mu du over dy. This is y direction. So you should take the derivative from this equation. We know that u is equal to u, capital U, times 2 y over h minus y square over h square. So du over dy is u times 2 over h minus 2y divided by h square. This is y axis. So here on the surface, we know that y equals 0. Okay. From equation 1, shear stress at the wall means meaning y equals 0 is equal to mu u times 2 over h minus y is 0, so 2 times 0 divided by h square. So tau at the wall equals mu u 2 over h, and it's easy now. So tau equals 2 mu, the viscosity of water, 1.12 10 to the minus 3 Newton per second meter square, times velocity u, which is 2 meters per second, and times 2 divided by h, which is 0.1 meters. So shear stress equals 4.48 10 to the minus 2 Newton over meter square. This was a really easy question. If you know what you're doing, it's not difficult to solve these problems. We have 2 more problems, this one and the next one. In this Question. We have two concentric cylinders. Sorry. Okay. We have two concentric cylinders, 6 inches long, so their length is 6 inches. The space between is filled with glycerin. We have the viscosity. The inner cylinder radius is 3 inches. We have gap between them with the thickness of 0.1 inches. Determine the torque and the power required to rotate the inner cylinder. So we want to rotate the inner cylinder at 180 rev per minute, and we want to find the torque and the power. The outer cylinder is fixed, and since we have a gap, the velocity distribution in the gap is linear. We already knew that, as I told you before. So this is inner cylinder. This is outer cylinder, which is fixed, and this one rotates. Here we have the gap with this thickness, and this cylinder rotates. This is the length of the cylinder, L, and yes, that's it. And here we have some liquid, which is glycerin in this problem. Okay, so we know delta is 0.1 inches. We know the viscosity, it's 8.5 10 to the minus 3 pound second per square feet. We know the radius r, ri, the inner radius, is 3 inches. We know the gap, and we know the omega, rotational velocity, which is 180 rev per minute. And that's it, I think. If this is a side view, actually it's a cross-sectional view. It's a cross-sectional of the system, and this is the top view. So if we look at the system from top, sorry, it's why I'm struggling with this. We can draw two cylinders, sorry, and another one. Okay, it's good. So this one, the outer one, is fixed, and the inner one rotates. Okay, and here we have velocity distribution, linear velocity distribution. Sorry, I think the rotation is this one. Okay, this is velocity. Here we have 0, and here we have Ri omega, and in between we have a linear distribution. From this we know that du over dy equals velocity divided by delta here, which is Ri omega is velocity, and delta is the gap thickness. And so this one rotates, and we have shear stress on this surface, on the inner cylinder. We want to actually we have shear stress on both surfaces, but we need to calculate the shear stress we have on this surface, because we want to find torque and power. So we only deal with this force, this shear stress. And as you know, torque can be calculated as F times R. Here F is shear stress, and R is the inner radius of the inner cylinder. Actually, this radius of the inner cylinder. Okay, there is no need to use integral, because at all these points the velocity is constant. We have the same velocity as Ri omega. And you know, force, shear stress force, is tau times area, and tau is mu du over dy times area. And when we have gap, this velocity gradient equals the velocity divided by the delta. So you should ask yourself whether these variables or parameters are constant or not: area, velocity, and the thickness of the gap. Viscosity is constant in fluid mechanics 1. It is mostly assumed to be constant, so it's not a problem. But you should think about area, velocity, and the gap thickness. We know the gap thickness is constant because these are two cylinders. If we have one cylinder and one cone, as you know, as you can see here, the gap thickness is changing here from top to bottom. So gap thickness is not constant, it varies at different points. And also velocity, here for example we had R1 omega, but here we had R2 omega. So in this case the velocity also varies. So if one of these, delta, gap thickness, velocity, or area, if only one of them varies from point to point, you should use integral. But here velocity at all these points is Ri omega. The gap thickness is delta, so du over dy is Ri omega over delta. And also the area, we know the area in this work, in this system, in this problem. Area is the circumference of the cylinder, 2 pi Ri times the length of the cylinder. So Ri is constant and L is constant. Okay, so there is no need to use integral in this specific problem. So torque equals tau area Ri. and tau is mu du over dy, and area, which is 2 pi r I L times Ri. So torque can be found as mu times 2 pi Ri square times length, and d over dy is Ri omega over delta. So torque is equal to 2 pi mu Ri to the power 3 L and omega, and in the denominator we have delta, and we know it's 0.1 inches. So you can easily calculate the torque. 2 pi mu is 8.5 10 to the power minus 3 pounds per second per feet square. Let me okay, it's better now. So this is mu. The radius is 3 inches. We should divide it by 12 because we need feet. Don't forget that. So 2 pi viscosity, Ri to the power 3. Length is 6 inches. So 6 divided by 12 feet. And omega is 180 rev per minute. You should convert it to radians per second. So we should do this. We know every 2 pi radians is 1 rev, and we know every 1 minute is 60 seconds. And in the denominator we have 0.1. Don't forget this 12. So divided by 12 feet. Torque is 0.944 feet pound. And we also need to calculate the power, P. P is T torque times omega. We know torque 0.944 feet times feet pounds, and omega, if you calculate this part separately, it's 6 pi radians per second. So this should be multiplied by 6 pi radians per second equals 17.8 feet pound over second. So this is a rather complicated problem, but I think you can solve it in the exam. It's not that difficult. Okay, this is the last problem. We are dealing with surface tension in this problem. Uh, okay, surface tension forces can be strong enough to allow a double-edged steel razor blade to float on water. Okay, but a single-edged blade will sink. Okay, uh, assume that the surface tension forces act an angle theta relative to the water. So this is surface tension force act uh, at an angle theta. Okay, it's not horizontal or vertical. Uh, the mass of the double-edged blade is 0.64 10 to the 0.64 grams. The total length of its side is 206 millimeters. Determine the value of theta required to maintain equilibrium between the blade weight and the resultant surface tension force. This is for section A. We have section B in this problem. Okay, let's start with section A. This is the blade. We have this force, the weight of the blade, and this is the force of surface tension. Here we have water. For water, surface tension is 7.34 10 to the minus 2 Newton per meter. It's really crucial, guys. Newton per meter. Surface tension acts on the circumference of the objects. Don't forget that. Okay, since we want the blade to be stationary, we should have the equilibrium of forces in vertical direction. So the summation of forces in vertical direction should be 0. We have two forces, the weight, which is downward, and here we have theta. So this is T sine of theta. Be careful, we don't have two forces. This is surface tension, one force, and it's acting on the circumference of the blade. So we don't have two T's. This is one force. So T sine of theta minus W is 0. So from this equation we can find sine of theta equals W over surface tension. W is mg, you know that. And surface tension force equals sigma, the surface tension of the water, times length of the object, of the blade here. And we have everything, so theta can be found as inverse sine of m, which is 0.64. I think it's here. Times 10 to the power minus 3 kilograms times gravity, 9.81 meter per second square. And in the denominator we have sigma, surface tension, 7.34 10 to the minus 2 Newton per meter, and the length is 0.206 meters. And from this equation you can find theta as 0.415 radians or 24.1 degree, 0.5 degrees. So it's not that difficult. Let's go to section B. The mass of the single edge blade is this much, 2.6 10 to the minus 3 kilograms, and the total length of its sides is, this means the circumference, as you know, is 154 millimeters. Explain why this blade sinks. Support your answer with necessary calculations. Okay, this is part A. Let's solve part B. Let's find these forces, omega and T. Oh, sorry, omega, it's not omega. W, weight, and surface tension. W is mg. M is 2.61 10 to the minus 3 kilograms times gravity 9.81 meter per second square. So the weight is 0.0256 Newton. And T is sigma times the circumference. And also we have theta here because it's not vertical. Yes, it's not T, it's T sine of theta. And you know sigma and the length and theta is 24.5, so the value of T sine of theta is 34 10 to the minus 2 Newton per meters, and the length is 0.154 meters sine of theta. Okay, so it's equal 0.0113 sine of theta. And you know that we have T sine of theta and W, the weight. So if you want to have equilibrium, or if we want the blade to stay on the water surface, T sine of theta should be greater than the weight. So sine of theta should be greater than W over T. This is T. W is 0.0256 and T is 0.0113. This is greater than 1. It's also greater than 2, actually. This fraction, I mean. So this means that sine of theta should be greater than 1, which is impossible. We know that sine of theta, it's equal or smaller than 1. But we should have this situation, which is impossible. This is the reason that single edge blade cannot float. And this is the way you can support your answer. And that's it, I think. This is assignment A of Fluid Mechanics 1, focusing on shear stress, viscosity, and also surface tension. So I think you, if you are, if you like these videos or find these videos useful, please like the video and share these videos with your friends. Thanks for watching this video. Until the next assignment, take care of yourselves and bye bye.